Tech Talk Tuesday.
Hello everyone and welcome back to another Tech Talk Tuesday. Today we're going to talk a little bit about safety when you're working with electronics. So I guess the first thing I want to start off with is, as an electronics technician and as an electrician, the two seem to have different definitions of what's considered high voltage and what's considered low voltage. In the electrical world, talking about electrical power, distribution power, things of that nature, your AC power that brings power to your home, into your home, transforms it so you can use it. That tends to have totally different what they consider high voltage. In the electronics world, usually anything over 48 volts is considered high voltage. 48 volts and less being low voltage, that kind of thing. In the electrical world, on the power side, which I've had to work in both over my career in the military. I've had to work on the AC side and the DC side, electronic side and the power side. And on the power side, you have anything up to, well, depending on what standard you look at, I think one standard uses 1,000 volts AC as the cutoff for low voltage. Another standard uses 600. Really, it doesn't really matter because there are no usable voltages really in the world between that 600 and 1,000 range. So whichever you want to go with. I kind of tend to go with 600 because all of your low voltage wiring is insulated to a voltage of 600 volts. So that's typically what I tend to go with. So anything 600 volts and lower is considered low voltage by the industry standards. And then anything over 600 volts or that 1,000 volts, if you want to go by that, and up to 69,000 volts is considered medium voltage. And then after that, there's high voltage, and then extra high voltage, and ultra high voltage. It just keeps on going. But if you look at the power line that's running on the power poles next to your house, with the transformer up there on the pole, or if you live in a neighborhood where your distribution is running underground, all of that voltage that's bringing power to your house is medium voltage. So it's running in the 13,000, 13.6 thousand, 13.8 thousand volt range, usually at that level of distribution. It's considered medium voltage. The voltage we produced in the Army was 4,160 volts phase to phase and 2,400 volts phase to ground, and it was still considered medium voltage. But I would actually work on equipment that had a potential transformer that would take that 4,160 volts or that 2,400 volts phase to ground actually, and take it and through a 20-to-1 ratio transformer and knock it down to 120 on the secondary side to operate the different metering devices that we had, the computer controllers, the whatever we had that operated on 120 volts or less would come through those potential transformers. So there was 2,400 volts on one side of it and 120 on the other with a 20-to-1 transformer. But so I was exposed to that 2,400 volts. So we had to, the key thing for us as technicians in that situation was safety. And I like to carry a lot of that on to the things that I do in the electronics world. Now, to me, working with that, because I know the dangers of working with that, the standoffs and what you have to do in that environment, I often think that it's overkill. But I don't want anybody to get the impression that the voltages you'll be working with in an amplifier, or if you think you're going to get into your amplifier and tinker around with it and you don't know what you're doing, I don't want to downplay that. But today we're going to talk a little bit about exactly why that voltage that you see in your tube amplifiers is dangerous or could be dangerous and life-threatening. One of the things we had in the Army, in our job, that kind of kept us reminded is a little saying called, as soon as you go to do any kind of work where you may come in contact with an energized source, is watches, rings, and shiny things. So we would always take off our watches, and it didn't matter that you couldn't get a guy that says, oh well, I don't wear a metal watch, I'll wear all plastic, whatever. No, it's just one of those things, you just take it off. Normally what we do is we take the watch off and we would put our wedding ring over the little band here, and then we would put our I used to wear a much thinner band here. This is one of these new fandangled smartwatches, but put our wedding ring over our band like this, latch it back in, and then we'd just stick this thing in our pocket so we didn't lose our wedding ring and come home and your wife be mad at you. But you'd rather come home without your wedding ring than without a finger or without your life. So, and then the biggest thing in the Army is we all wear these dog tags, and so we'd take these off and put them in our pocket. And so if you're working over something, even like on your bench or something, and you're wearing your dog tags, you reach over your whatever you're working on, and these fall out into the whatever you're working on. That wouldn't be a good deal. So we'd always take these off. So those are the big things: watches, rings, and shiny things. So a lot of you guys that got the same training I did probably have heard that saying before. But anyway, so you hear a lot of people say, hey, you got high voltages in here, it's dangerous, it could kill you, all this stuff, and that's true, it can. But I think the biggest threat you have is sticking your hand in there and getting that ring or something that you have conductive on your body in between a component and the chassis or something like that, and shorten it out. You really have a much greater propensity, I think, of that happening. So some of the things you can do to mitigate that is, first of all, whatever you can do on the amp with it completely de-energized and with all your capacitors discharged, so there's no voltages whatsoever on your amplifier. Anytime you can work on your amplifier in that state, do that. The second thing is, if you absolutely have to work on an amplifier with it energized while you're troubleshooting, which sometimes it is necessary, oftentimes it is necessary, use something non-conductive to probe around or do whatever you have to do in there. They even make non-conductive screwdrivers if you have to actually get in there and tweak something. I would recommend that. What you're touching with the screwdriver may not be energized, but that screwdriver shaft can come in contact with something that is. So that's the threat there. Also, if you absolutely have to stick your hand in there for whatever reason, first of all, you should know exactly what you're doing when you do this. But if you have to stick your hand in there for whatever reason, the rule of thumb, or I guess the common procedure to use, is to always have like your other hand totally off the bench. Some people like to use stick the other hand in your pocket type of thing, where you're only working with one hand. What you never want to do is have that chassis in this hand while you're manipulating it somehow, and then feeling in with this one. And we're going to look at some diagrams here in a minute, and it'll kind of tell you why you don't want to do that. So let's look at some things that's going to show you. So the main thing is, you have this voltage and you have a resistance in your body. And because of the voltage that you're working with, whatever it is, and the resistance in your body, you'll have some sort of current. And that's really where the danger comes in. That's what can stop your heart. That's what causes the burns. It all boils down to current. How much current is going to run through your body. So it's not the voltage at all, really. It could be a very low voltage if there's enough current and because your body has if your body has a low resistance at the time. So it's not the voltage that's the issue, it's the current. So we're going to look at some things, and you'll see exactly what I'm talking about. So let's go over to the diagram. Okay, so on this little chart here, it gives certain values for different amount of current and what the effects of that current is through the human body. Up here, 100 milliamps or less, it says causes no sensation, not felt. So you can't even tell if 1 milliamp or less goes through the body. The threshold of what's called sensation is 1 milliamp to 8 milliamps, depending on the person, on what they can feel. Really doesn't do anything to you, you just kind of feel something. So that's the threshold current. It's still safe since it's not affecting any muscular control or anything like that. Anything from 8 to 15 milliamps, painful shock, but you still have your muscular control, you can let go. 15 to 20, that's when it starts actually affecting your muscles, and it's very painful, and the victim usually cannot let go because of the muscular control loss. 50 to 100 milliamps can take a person into ventricular fibrillation. That's where your heart, basically it messes with the electrical rhythm that is causing your heart to beat, and you could die. And that's 50 milliamps to 100 milliamps. That's typically if the current actually flows through the heart to disrupt that. We'll talk about that here more in a minute. 100 to 200 milliamps, ventricular fibrillation occurs. Most of them, like this right here, 50 to 100 could occur. It has occurred in some people. This, it's definitely going to occur. And then over 200 milliamps, you're going to get severe burns. All of these other things are going to happen, more than likely. Heart stops, and severe burns, so severe that chest muscles clamp the heart and stop it for the duration of the shock. So your heart basically stops in this, not just the ventricular fibrillation, which is, basically a change in your heart rhythm. It stops completely, thus preventing ventricular fibrillation. The next thing I'm going to put up here is a resistance chart of the body, and we'll talk about that. Okay, so you could probably go on the internet right now and look up human body resistance or something like that, and you'll come up with about probably 500 different versions of what the human body's resistance is, and each one of them tries to duplicate it in a different way. When I was going through school, this was what was considered the kind of the model for the human body resistance. Now, the skin, I think, is the highest resistance in the human body, and but depending on the circumstances, the skin's insulation value can actually break down rather rapidly, and once you get past that, the resistance of the rest of the body is fairly low. So, and then the resistance of the skin and everything is completely dependent upon the humidity, the hydration of the individual. The different people's skin, believe it or not, is actually thicker than others. When somebody says they got thick skin, well, they could literally have thick skin. So none of these values are set in stone, but this is generally what is used to determine how much current could travel through the body. So from arm to arm, which would be right through your heart area, which would definitely lead to that ventricular fibrillation. So it looks like 500 ohms and then another 500 ohms in series would be 1,000 ohms. If you're working on a 400 volt B plus rail in your tube amp, that means, and you get in contact with the chassis to that B plus voltage, you could possibly get, according to Ohm's law here, 400 milliamps through your heart. So that would probably definitely stop your heart, and you could have severe burns and stuff like that. Now, typically for this to happen, you would have to have a really low skin resistance at the time, meaning something would have to be leading to that really low skin resistance. Maybe you got a slight cut that's a direct direct path into the soft tissues of your body past that skin. Maybe you're very hydrated, or a lot of different things can lead to different skin resistances. So the temperature, everything. So you never know what those conditions are. But even if you look here, all the way across your body through your feet, that's just an extra 100 ohms through your soft tissues of your body. So once you break that main barrier of your skin, you're pretty low resistance through your body. The general rule on skin, usually on most things that I've heard and read, is 10,000 ohms. So if you wanted to say that your skin has the maximum amount of resistance that it could have, or the average amount, I guess, at 10,000, you're still looking at 40 milliamps possibly going through your body at this stage. So yeah, you're working on amps with 400 volts in it. Now obviously if you're working on something with 350 or something like that, this goes down because you're dividing into a smaller number. But if we take this and put this back up here, you can clearly see that anything in the 15 to 20 is going to give you a painful shock. So, and then this 50 to 100 area here, that's when you could die, possible death. And if you may ask yourself, well, how do they know these things? Well, because they actually tested this on people at one point. When they were experimenting with the causes of electrical effects, they actually tested this on people. Hey, when do you feel this? Oh, okay, well that's 2 milliamps, or that's 1 milliamp, and you can feel it. So that's where they came up with these values here. They actually did this. Now, whether people died during these experiments, I don't know. Maybe they had somebody there to resuscitate them or something, but this is where they come up with these values. So I don't want to downplay in any way the significance of the voltages that you're going to find in a tube amp and the dangers that they pose. I just wanted to give you guys an idea of why, when somebody says that it's dangerous, why it's dangerous, and not just, hey, it's high voltages, which people use that term all the time. It's a higher voltage than what most electronics run at, but it's not a high voltage. But it is something that can definitely kill you, because as I've actually shown you, it just takes mere milliamps to possibly kill you. And just 1 milliamp, you'll be able to feel it. So not only that, but you can cause damage to your equipment by shorting things out. So you just need to practice caution. If you use those 3 things I talked about earlier, working with the equipment de-energized and discharged, working with insulated equipment, probes, etc. And then if you absolutely have to stick your hands in there, just using the one hand rule, where you're not touching anything else with the other hand, giving it a path through your heart, you will be safe. So I don't want you to go out there and say, hey, I watched a video on how to be safe, so I think I can do it now. I'm not saying that. You may want to get a little more training, because you can know all of the things that I just told you and still not know exactly what in the amplifier is holding those voltages and what's not. And so that's a whole nother thing that you have to learn. But I hope you guys enjoyed this and found it a little bit educational. If you already knew all these things, I hope it at least heightened the awareness a little bit, and you'll keep safety in mind when you're working on your gear. And look out for next week's Tech Talk Tuesday, and please hit subscribe and that little bell next to it, and it'll give you notifications. And go ahead and like this video, and I appreciate you tuning in. Thank you.